Okay, so here are the slides for today's lesson. It says day 16 on the on the slides. I had combined 16 and 17. I put all of the sampling and sampling distribution stuff together just to save paper. So you probably have these printed out. If not, obviously they're posted on BlazeView. Just a review. So we had talked about sampling, what a population is, the difference between, so when we're talking about a statistic, we mean we're referring to something, a measure to describe a sample versus a parameter, which is a measure to describe the population. Some of the different notations, the Aramaic versus Greek lettering, a little bit about probability, what that is, probability sampling, what a simple random sample is. So this stuff, it should be clear. Obviously, if you have any questions, let me know, but this is kind of where we left off. So the one thing I'll say too is keep in mind when I'm talking about sampling distribution stuff today, recall Michelle or Dr. or Miss Pratt's example from class. So the last day we had class, the SPSS example, where you took samples of different sizes and collected the means and looked at whether it was within the confidence interval. Just recall that example because it is, I mean, it's exactly what we're talking about today. I've got an example of my own and an example from the book. If you would like more information on it, there's a ton of YouTube videos on this. I've linked a couple at the end of these slides. So if you want to hear somebody explain the exact same thing, you just using different words, that's available to you. So anyway, that's there. Again, the book, I can't stress enough to make sure that you're reading the book. Okay, so sampling distribution. So kind of the key to all this is to understand that there is a true number in the population that we're always trying to estimate. For example, in the United States, there's 328 million people, say 330 million people, and there is an average, say, height out there. We could measure the height of all 330 million people and get their height and add them all up and divide it by 330 million, but typically we don't do that. We collect samples. So we're always trying to estimate this true population mean that's out there. However, a sample is always going to have a little bit of error, and you've seen this before. Think about when you see like polling data. So a certain candidate is polling at 52%. And then you see plus or minus, say, 3. Well, what that indicates is that with any kind of sample, there's a degree of error. And what I'm going to show you today is sort of theoretically how we can disentangle that error and understand how large, how small it is, and some of the factors that go into creating a small, what we're eventually looking at is a confidence interval that with sampling error. And the factors that kind of go into how large or small that is essentially. So a couple definitions: sampling error, the discrepancy between a sample estimate of a population parameter and the true population parameter. So that would be like I said, say candidate A is polling at 52% plus or minus 3. Well, that sampling error would be the plus or minus 3 because it indicates a degree of uncertainty around the estimate that we have. We'll get into that a little bit more in detail as we go in the next chapter when we talk about estimation. Again, this is all kind of, obviously it's a linear class, but we're setting up for what we'll talk about Thursday and Tuesday, which are estimation stuff, and you'll have an assignment on that. Okay, sampling distribution. This can be a little bit tricky for people to understand, but bear with me. I think we'll kind of flesh it out here, hopefully. But a sampling distribution is this theoretical probability distribution of all possible sample values for the statistics in which we are interested. To put that in more simple terms, recall the example from Miss Pratt where you did I can't remember if it was 3 or 5 samples that you took from the population of data in the GSS. It was basically assume that the GSS was a hypothetical population and you took samples from it. So you had a sampling distribution that you created where you had several means that were generated from the samples. Now they were all trying to estimate that one population parameter, but they were slightly different because the samples that you took had different people in it, so you're going to get a little variation in it. But that's sort of what was going on with the sampling distribution. You can think about as a distribution of possible sample means. So up until this point, we've done things like frequency distributions where we look at values for one variable in one sample. This is different in that we're not looking at values for one sample, we're looking at means for multiple samples. We never really observe this because typically, like in social research, we don't take many samples, basically because of the theory that I'm going to get to, the central limit theory, which is kind of the so what of this whole lecture. But I'm going to show you how it works so that when we do it, moving forward, when we do inferential statistics, you can be confident that your estimations are correct. Okay. So let's start with the example. I think it's the easiest way to get going, especially considering how we're learning these days. So this is straight from the book. So imagine that you had a hypothetical population of 20 people, okay? So desert island, there's only 20 people on it, that's your population. And we go and we get the income in dollars for these 20 individuals. I guess this desert island uses dollars, so just assume that. So if you look, we can see these individual cases. So person number one makes $11,350. Person number two, $7,859. Person number three, $41,000, so on and so forth. So you see some variation. You can, just kind of eyeballing it, you can see your range is between, I guess we got 7,000, I think that's the lowest. That's 7,859. And then the highest, I'm seeing a 68,100. So, you have variability there. We've talked about the measures of central tendency and variability. We can get the mean. There it is right there. 22,766. Now note that that is mu, the U with the little tag on it, the Greek letter mu. That's the population mean. So that's a parameter. Because remember, these 20 cases, this is our population. Same thing with the standard deviation. We've got a sigma there, 14,687. That's a population parameter too, okay? So again, this is a hypothetical example. You can think about in the United States with 330 million people, typically we don't know the population mean. That's what we're trying to estimate. Again, I'm just showing some hypothetical examples so you can buy into the fact that this estimation stuff works. Okay, so back to our 20 people. So we've got our population mean here, standard deviation here. So this describes the central tendency, right? Variability. Okay, so what am I talking about when I'm talking about the sampling distribution? Well, just to kind of refresh you, population mean versus sample mean, our notation, X bar versus mu. Population standard deviation, sigma, sample standard deviation, S. What's S squared? That's the variance, just as a reminder. That's a little translational piece, but just to kind of refresh you on that. So suppose that we take a sample of 3 individuals from the population, okay? So I randomly chose case number 5, case number 15, and case number 17. And as you can see, if you look at case number 5 here, 17,458. Case number 5 here, 17,458. So we just took samples of 3 people from this whole population. We chose 3 out of them. And we did that twice, okay? So again, think back to your example with Miss Pratt. This would be like the GSS population. These were the little samples you took out, just 3 this time. So the question is, what is the sampling error? Or what do we gain from sampling in general? So I worked it out on the paper here. So here's case number 1. Or I'm sorry, I shouldn't say case number 1, example 1, with case 15, 5, and 17. So I've written down the 3 income values, right? Okay, and added them up, divided by 3, and I got my sample mean of 21,345. And then I did the same thing for sample 2, okay? Case 8, 16, and 17. Took all 3 of those, added them up, and divided by 3, and I get 20,817.3. Okay, so the question is, how well do these estimate the true population number? Well, 20,800, 21,345, they're both kind of similar, but we know what the population mean is, right? In this example, we know that it's 22,766. So that's pretty good. The question, though, is how good is pretty good and how close is it? And that's what we're trying to get to. But essentially, you can look at this true population mean and these sample means that we generated and see that they're relatively close. And it makes sense, obviously, because what is the population but a collection of all the samples, right? So when we take the samples, obviously they're going to be at least sort of close, but you could imagine a hypothetical scenario where I randomly select case 12, which is 68,000, and case 3, which is 41,000, and case 14, which is 47,000, and I get a much higher number. So I could, and likewise, I could maybe randomly select lower numbers, or cases with lower numbers, like case 6, and get a lower sample mean than the true population mean. So that's possible too. But the point is that if we, well, hold on that. Let me get to that eventually. Sorry. One thing I will say is that the crux of this relies on random sampling. You can't just choose 3, the first 3 or the last 3 or the highest 3. They have to be randomly selected. So using a random number generator, some kind of randomness. That's the key with the probability statistics, is that every person has an equal chance to be selected. Okay? All right, so let's go back to our cases. So again, the essential question is, what is the sampling error for these 2 samples? Okay, we can figure out the mean, but we want to know how accurate the samples are. Well, it all kind of relies on this basic idea, and this is very theoretical. It can be a bit confusing. Bear with me. I think, kind of doing some examples and thinking about it, I think it'll become more clear. But the idea is that if we have what's called a sampling distribution of the mean, okay? So imagine hypothetically, if we derived, so back to the example here, if we kept taking samples of 3, okay, so I did 2 examples where I took samples of 3, but what if I continued to take samples of 3 from this population? Well, we could theoretically draw up a distribution of all the possible means that could be obtained by drawing the population, by drawing from the population all possible samples of the same size. So I know that sounds like a mouthful, but imagine if we kept taking samples of 3 from this population, and we did it infinitely until we covered all possible instances. I don't want to do the math of how many that would be, but trust me, it would be a lot. So if we had this theoretical distribution of all the possible means that are obtained by drawing from the population, then you could imagine how we could plot a frequency distribution of sample means. That's the sampling distribution of the mean. It is basically a distribution of all these sample means. So again, we're not plotting individual values. Like here, we wouldn't be plotting these values themselves. We would be plotting the sample means, well, which I've generated here. So imagine if I kept doing this over and over and over again, I would get a bunch of sample means. So I could plot those sample means in a distribution, and eventually what I'd end up with would be a normal distribution around the true population parameter. So take a look here. We've got mu right at the middle, and then mu minus 3, mu plus 3, mu plus 5. So again, these are kind of, these are hypothetical numbers, but imagine as we kept taking samples, we'd eventually arrive at a normal distribution around the true population parameter, mu. Okay? So, take a look at this example and see if this makes sense. Let's work through this word by word. So, from a population of raw scores, that's these right here, so population of raw scores, in this case income, we draw m samples of size n and calculate the mean of each sample. So we determine the sample size. So in this case, we're using 3, though that's there's no rule about 3. You can take a sample of any size. Eventually, what you're going to find out is that samples of larger sizes are more accurate, obviously, because as you approach a sample of with everybody, then you arrive at the true population mean. So we draw m samples, so multiple samples of size n, and calculate the mean of each sample. The resulting sampling distribution of the mean based on m samples of size n shows the values that the mean could take and the frequency associated with each value. Again, that's this distribution here. So we plot the sample mean around linearly, and as we continue to take more and more samples of size n, obviously, so here we are adding up all the raw scores, getting our x bar. Your book likes to call it y bar, but let's be consistent. X bar is this is the sample mean. Here's another sample mean, another sample mean, another sample mean, over and over and over and over again. The sampling distribution is going to approximate a normal curve. And what's interesting about that is it works even if the data itself is not normally distributed. Some of you might be thinking, well, income is something that is highly skewed. We know that. But the sampling distribution of the means, plotting all the sample means, all the possible sample means of size n along a line, we're going to find that it lines up normally, and I'm going to do, hopefully, so here's one example, and I'm going to do another of my own, but this is the one from the book. Please make sure you read this. Okay. So, we denote the mean of the sampling distribution as mu of x bar. Essentially, and this is gonna be troublesome for some of you, but bear with me, it's the mean of means. So back here, we took one sample and got a mean, another sample and got a mean, another sample and got a mean, another sample and got a mean. Imagine if we collected means, we did this 1,000 times, we got 1,000 different sample means. Well, we could take the average, which, some people quibble with, let's average in terms of the mean. We could get a mean, which would be the, sort of the collective average of all the means, which I know sounds kind of silly, but if you think about it, think about taking the mean of the sample mean. So in this case, we took 2 samples. So here's one sample mean, here's another sample mean. I could get the mean of means by adding these 2 together and dividing by 2. That would be a mean of 2 means. Okay. So the mean of the sampling distribution is obtained by adding all the individual sample means and dividing by the number of samples, just like we did here. I mean, this is just so here's the sample means and dividing by 2. We only got 2 sample means. But imagine hypothetically, and this is in your book, that we took 50 means, okay? So here's the first, and the second, and the third, and the fourth, and the fifth, and we took 50 samples of 3, got 50 means, and then added those sample means together and divided by 50, which was the total number we took. So this 24,750 is the mean of means. And, you know, if the word average works for you in terms of making sense of the mean, it's the average of the means, okay? So that's kind of part one. And if you recall, there's always two parts in statistics. We always want to look at the central tendency and the variability. So we've looked at the central tendency. In this case, we're talking about the central tendency of the means themselves. So we got a mean of means. So that's our measure. The sampling distribution of the mean is the measure of central tendency for all possible samples. But we also want to know something about the variability. So, and that's what we refer to as the standard error of the mean. So the standard error of the mean is the standard deviation of the sampling distribution of the mean. So it describes how much dispersion there is in the sampling distribution of the mean. Again, so if we plotted all possible sample means across, linearly, just like this, and we took these sample means and divided by the total number of means to give us our mean of the sampling distribution. Well, we would also want to know something about how variable are the sample means around the true population parameter. That's what we refer to as the standard error of the mean, okay? The standard error of the mean is pretty easy to calculate. Note the notation too, sigma x bar. So it's kind of like the standard error of the sampling distribution. In other words, the standard error of the mean, mu x bar. Similar to how the mean of the sampling distribution was mu x bar. I'm sorry, I misspoke. Sigma x bar, this is our variability measure, versus mu x bar, our central tendency measure of the distribution. So to calculate that, again, this is the easy part. The standard error of the mean is equal to the standard deviation, right? The population standard deviation. Note that this is a Greek letter, so we're talking about the population standard deviation divided by the square root of n. Okay, what's n? It's the sample size. So to get the standard error of the mean, again, the calculation is pretty simple. So go back to our example. In our hypothetical example, we know the population mean and we know the population standard deviation, 14,687. So in order to get the in order to get the standard error of the mean, we just take our population standard deviation, 14,687, and divide by the square root of 3. That was our sample size. Took a sample of 3, okay? 8,470. Now, if I had the chance to go back and do this, I would probably make sure I added in the units. These are in dollars. We're talking about income distribution. This is all in dollars or whatever kind of income they use on this desert island. But our standard deviation units are always the same units as what we're analyzing. Right? Okay. Okay. So let's just look at these two figures and see what's going on. So the first is the population distribution of personal income for 20 individuals. This is what you've seen before. This is taking all these people and plotting them on a frequency distribution in terms of their income. You did this. This was chapter 2 or 3. This was on the first exam. Plotting a frequency distribution. Now what's different here in part B is that this is the sampling distribution of sample means of sample size n equals 3. So this is the distribution of the sample means of sample size 3 drawn from those 20 individuals. So this is a sampling distribution. So see here, we have this is not a normally distributed variable at all. It's highly skewed. Same way as the United States is, where you have a bunch of clustering at the lower levels and then some high outliers. But when you we took a hypothetical example of 20 individuals' income. We took samples of size 3 of this population of 20 individuals' income, and then we plotted these on the distribution. So, oops, sorry, I hit the back button by accident. So these are sample means that we that we've plotted here. So it'd be like when, again, back to the example, sample 1, here's a mean. We plot it on the chart. Sample 2, here's another mean. Plotted on the chart. Okay? So as you can see, this approximates a normal curve much closer than this one with sample size 3. Now what happens if we take a sample size of 6? So again, back to this example, we took sample sizes of 3. Well, what if we chose sample sizes of 6 from the population and got a mean? So we did, rather than 3 people, we got 6 and got a mean for sample 1. And rather than 3 in sample 2, we took 6 and got a mean for sample 2. So if we plotted that on a distribution, zoom out here, we'd get an even closer approximation of normality. So what you should kind of be picking up now is that as the sample size increases, the sampling distribution not only becomes more compact, it becomes more normal. And when I say compact, really what that relates to is it lowers the standard error. So think about hypothetically, if we have this population of 20 people, get back to it. What if we took a sample size of 20? Well, that would be everybody. We would get the sample mean every time. There would be no sampling error because we get the exact population number every time. But what if we only took a sample of 1? Well, we could end up with something like 22,545, like in case 10. That would be really close to the real number, to the true population mean. However, if we took a sample of 1 and we got case number 12, we'd be way high. Or case number 6 would be way low. As the sample size increases, your sampling error goes down. Okay. What this all leads to, let's see, where are we? What this all leads to is the reason we can do inferential statistics is because of what's known as the central limit theorem. So let's read through this and work through it logically. So if all possible random samples of size n are drawn from a population with a true mean mu and a true standard deviation sigma, then as n becomes larger, the sampling distribution of the sample means becomes approximately normal, with the mean, so mu x bar, which is the mean of means, equal to the population mean and a standard deviation equal to the sampling distribution, equal to the standard error of the mean. So, what does that really tell us? Well, as we increase our sample size, our estimates become more accurate, and that shouldn't be surprising to you. But the question is, how accurate? Well, because we know that with this hypothetical sampling distribution, we know sort of how things behave. So what this, the key, I don't know that the key, but an important aspect is that the significance of this, a big part of the central limit theorem is that it tells us that with a sufficient sample size, the sampling distribution of the mean will be normal regardless of the shape of the population. Case in point right here, right? Once we increase our sample size to 6, our estimates were much more normal and they were less spread out, as was, compared to figure B right here, okay? So even though the population distribution is skewed, we can still assume that the sampling distribution of the mean is normal, given that the random samples are large enough size. Okay. So, just to kind of rephrase that, the central limit theorem tells us that as the sample size gets larger, the mean of the sampling distribution becomes equal to the population mean. And I think, you can logically think about that. So if that population of 20, if we took a sample size of 10 or we took a sample size of 18, which do you think would more accurately represent the true population parameter? Well, the sample of size 18. And I mean, think of it another way. If we took a sample of size 20, which would be everybody, we would get the true population mean. Versus if we only took a sample of 1 or 2, there's a lot more variability there. And if we plotted those sample means with the different sizes, so 3 in this case, we get a lot more spread, even though it does start to approximate a normal curve, even with a small sample like 3, we get a lot better approximation with a sample size of 6. Okay. Point number 1, as the sample gets larger, the mean of the sampling distribution becomes equal to the population mean. Okay. That's the central tendency part. Again, we always talk about the average and the spread. That's kind of, a lot of statistics comes down to, what's the typical number and what's the variability within it. So in terms of the sampling distribution, the mean of means, or the mean of the sampling distribution, aka the mean of means. I'm sorry, I lost my place. As the sample size gets larger, the mean of the sampling distribution approximates the population mean. The variability side of that is that as the sample size gets larger, the standard error of the mean, aka the standard deviation of the sampling distribution of the mean, right? So the measure that the standard error of the mean describes the variability in the sample means, it decreases in size. So it makes sense. If larger sample sizes, they're going to give you a more accurate representation of the typicalness, and it's going to give you more accurate representation of the true population parameter in terms of its spread. You're going to have less variability. What that equates to, back to the voting example that I used before, if I had, say candidate A was polling at 52%, plus or minus 3, and candidate B was polling at 52%, plus or minus 10. Well, we could assume that the first example probably had a larger sample size because there's less variability in it. 52 is the central tendency measure, but plus or minus 3 versus plus or minus 10, we're a lot more confident in our estimate for the first example. So we would assume that would probably have a larger sample size, and typically it does. So as the sample size increases, the standard error also decreases. So kind of to sum up again, the standard error, the mean, tells us how much variability in the sampling estimates there is from sample to sample. Okay, so the standard error tells us how much variability we would get in, say back to our hypothetical example of the desert island, the income stuff. It tells us about how much variability we can expect if we took a different sample of size 3. So I took this one and this one. That standard error that I got, we calculated already, was 8,470. So that tells me something about the spread here. So plus or minus 8,470, if we added and subtracted those, we're going to be at about 12,000 to 8,000. It's going to be closer to 30. So as long as we would expect typically we would expect our estimates to fall between $12,000 and $30,000. That's a pretty wide range, and it's due to the fact that we're taking a small sample. It's only 2. If we increase that, we tighten that measure a little bit. Again, think back to Ms. Pratt's example. That's illustrating exactly what I'm talking about here. Okay, so many of you might be wondering, what is a large enough sample size? Well, there's really no hard rule on this. It kind of depends on the population size. With a population as small as 20, even a sample of 4 or 5 would pretty well get you your, would be pretty accurate. But typically, in real life, we don't have populations of 20 usually. There aren't many things I can think of that are that case. Maybe the population of our classroom, it was 25. So I don't know, but typically we have populations that are a lot larger than 20. Again, no general rule, but usually, and I could go into the math to show you this, but I don't think anybody wants to see it. If you do, you can let me know. I'd be happy to share the proof with you. But typically when you have a sample of about 50 or more, the sampling distribution of the mean becomes approximately normal, regardless of the shape of the distribution. So as long as you have a sample of about 50, you can assume that you have a relatively normally distributed sampling distribution. So even though the distribution of the variable itself might be, it might be skewed, it might not be normal at all. If you get a sample of size 50, we can assume that the sampling distribution, this hypothetical distribution of if we continue to take samples over and over and over again of size 50, would approximate a normal curve. Okay? If the population itself is normal, so imagine that we took a normally distributed variable, so something like, I don't know, height. I mean, height would be an example. The mean height of women is about 5'5", men is 5'8", 5'9", something like that. 50, that would be your kind of mean and median. If you have a normally distributed variable, then a sample as small as 30 will give you a normal sampling distribution. Again, you don't need to memorize this, but these are just sort of general rules that we use. So if we have a normally distributed variable like height, a sample of 30 should do it for us. If you have something skewed like income, you're going to need a larger sample to do so, about 50. And in the examples that I'm going to give you and everything we do from now on, I'll always make sure to give you a large enough sample so you can calculate. I know some of this is going to be a little bit fuzzy to some of y'all. Like I said, watch this, these couple of videos I've linked. Ask me questions. I'm willing to go through some other examples. I've got one example to do here after I finish the slides that hopefully will help, and we'll just kind of go from there. If it's it's one of those things that if it's too fuzzy, if it's really causing you issues, it's one of those things that you're just gonna have to kind of buy into. Mathematically, it works, but the essence of inferential statistics is the central limit theorem. That's kind of the crux of everything. Theoretically, if this wasn't the case, then we couldn't, think about it. We couldn't take a sample from a population and say anything about the population because it would just be a collection of numbers. We can only do so because of the central limit theorem. So what? Here's a bunch of, kind of maybe some word vomit from me. But just, I know it's abstract. It's going to take a little bit to sink in. So review the 20 incomes examples from the book. Check out these YouTube videos. Ask me questions, and stay tuned for my little demo here that I'm going to do right after this. So the key, though, is that last bullet point. So if we know that the sampling distribution is approximately normal, then we can always use our standard normal table, the z-table, to determine the probability that a sample mean will fall within a certain distance of the true mean. So we'll always be able to tell whether our estimate is something that we can expect given the sampling distribution. Again, think back to Ms. Pratt's example. Okay, so that's it for the slides. I'm gonna stop this video because we're already at 40 minutes. And I'm going to do another quick demo, which hopefully will help some of y'all out. So goodbye, and I'll see you here in a second.